So here, what we're going to do is discuss a problem about taking the SAT. And what we've been told is this. Usually when you take the SAT the first time, and then you take it again the second time, as a result of taking it the second time, you do a little bit better because you've seen the test once already. So that's generally a true rule. All right, so what we're interested in here is looking at a comparison between your second test score and your first test score. So we're going to start by saying this. Let mu equal the average difference between the second SAT score and the first SAT score. Now, in every one of these problems, when you start off, you should write down what you think mu is going to represent. The question you should ask yourself is, what do you suspect about this mean, this mu, if people are really scoring better on the second administration exam than the first? So we suspect mu is greater than 0. And that would make sense, because if I took the second SAT score and subtracted the first one, since the second one's a higher score, the difference should be positive. Now, when it comes to hypothesis testing, we want to state this in the form of what are called a null and an alternative hypothesis. So the null hypothesis is always denoted with H sub 0, the null hypothesis. And the null hypothesis usually indicates that there's no change, that there's really no difference between the first score and the second score. Okay, or it's a claim maybe that someone's making. In this case, we're going to say that there's no difference and that mu is equal to 0. Now, the alternative hypothesis is what you suspect is probably true, or what you as a researcher are hoping to find evidence for. So in our case, we think that mu is actually greater than 0, because we think if the kids go and take this test, that after taking it, that they're going to do better the second time, and therefore when we do the second score minus the first score, it's going to be something positive. All right, so in this problem, we were given some information. Number one, we're given that the population standard deviation was 50. Okay, you'll notice that the problem we did with confidence intervals and now these significance tests, in both problems, you were given the standard deviation of the population. Okay, that's a good thing to know. In the future, we'll talk about what you do when you don't have this. If you're thinking to yourself, hey, it's kind of ridiculous, how would you know the standard deviation is 50 but not know the true mean difference? That's a legitimate complaint. Okay? So just keep that in mind. We'll get to that eventually. Now, additionally, we're given information about 46 students. So N is 46, and they told us all their differences in test scores. So, for example, some of the data points look like this. -30, 24, -43. To name a few. It's important to know what this means. This -30 means that the second try minus the first try equaled -30. So this particular student here actually did worse the second time around by 30 points. This kid did 24 points better. Okay? If anything, this kid that I circled in red might start to provide a little bit of evidence that HA might be true, that the true mean difference is something positive. Okay, now, we have lots of data points. If you took the time to average them all, I will save you the stress and tell you that the average of all of these is x bar equals 13.36. So the average difference in this group of 46 kids between their second score and the first score was 13.36 points. The question we want to ask is, or answer is, does this constitute enough evidence that the true mean difference between the second score and the first score is greater than 0? Okay, so after you stated your hypotheses, the other thing you always do is talk about assumptions. So you should always list them out here and give them a try. Number one, did you have an SRS? And yes, you did. They said there were 46 students selected at random. Number two, this test is called independence. What you really need to check is the population greater than 10 times your sample size? In other words, do you think that more than 460 kids took the SAT twice? And we're going to say yes. Okay. And also, don't forget, that's also the check for the sigma of x bar equals sigma of x over square root of n. So that's nice to know. Also, we're going to need that. And then the last thing you need to check for is the normality of the distribution of x bar. But in this case, we get it. So in this case, we kind of luck out. Since n is greater than 30, we can say the central limit theorem guarantees or tells us that x bar is approximately normal. Okay? That's good to know. Now, let's be a little more specific. The mean of x bar should be 0 because we're operating under the assumption, as stated by the null hypothesis, that there really is no difference between the second score and the first score. This whole test is being done under this assumption. All right, so let's proceed. So it's going to be normal, and the standard deviation, don't forget, you get that by doing sigma of x over rad of n. Or in our case, sigma of x was 50 over the rad of 46. Okay, so there you go. Now we're ready. We're going to start making our picture. Step 3. You draw your normal distribution. You put whatever your null hypothesis says in the middle. So in our case, mu is going to equal 0. Now, we know we have an x bar of 13.36. And we know I have a standard deviation of x bar of 50 divided by the square root of 46. So the question is this. Do you think x bar is far away from mu equals 0? Or do you think it's close to mu equals 0? And how do you make that decision? All right. So this standard deviation is about 7.37, which means that our x bar is almost 2 standard deviations away. Not quite, but close. So it's pretty far out here to the right. So I'll put x bar equals 13.36, and we'll label it. Okay. Now, when you shade this, you should always shade as extreme or more extreme than x bar. So the question is, where do you go where you'd be even further away from the mean than our x bar already is? And that would be to the right. Okay? You notice we don't shade over on the left at all. That's because we're only interested in whether or not mu is greater than 0. So let's keep going. All right. So let's calculate number 4, something called the z-test statistic. But if you look at it, this should seem very familiar. Sigma of x over square root of n. Well, if you look at it, it looks just like a z-score, doesn't it? And if you look at the thing on the bottom, what is that? Sigma of x bar. So this is really x bar minus mu of x over sigma of x bar. Or we can plug in our numbers. 13.36 minus mu, which is 0, over 7.37. If we divide those, we should get 1.8, 1.81 maybe, something like that. All right, so now, what do we know? We know that this x bar is 1.81 standard deviations above the mean. Well, if I know that, then I can get something called the p-value. So let's just define the p-value. P-value is the probability of observing our x bar or something more extreme. Oops. Than our x bar. So So in our case, we can write that as the probability that x bar is greater than 13.36. Yep. Or really, probability that z is greater than or equal to 1.81. So I think you're going to get something about 3.3%, something like that. All right. and just to be clear, the p-value is this area. So 3.5% or 3.3%, whatever I said it was. Okay, so now let's make a statement. We need to explain what this probability means. Okay? What this is saying is that the probability of observing an x bar of 13.36 or larger when the true mean difference between the second score and the first score is 0 is 3.3%. So this 3.3% is really a very small number, okay? And usually we use an alpha level, use alpha equals 0.05. 5% is usually the magic cutoff. So 3.3% is less than 5%, and that's going to imply the following, that we're going to reject HO in favor of HA. And HA states that mu is greater than 0. Now sometimes after doing all this work, you'll forget what mu represents. So let's just go back and remember what mu was. Mu is the average difference between the second SAT score and the first SAT score. And we've just found evidence that mu is greater than 0. So if the second score minus the first score is something greater than 0, and we've just proven that, then that means that the second time you take the test, you are going to do better, and that HA is more likely to be true, and we can reject HO in favor